Welcome. This is lesson 1 of Unit 7 on logarithms. In this lesson, you're going to have a better idea of what logarithms are, much better idea. We're going to look at some of the characteristics of logarithm functions, how they are the inverse of exponential functions. Then we're going to go into the next example, just defining logarithm functions. How we get them, what they're really based on, some little special things about them. And then we're going to evaluate logarithm functions, and the very last thing is we'll graph them. And you'll see they're nothing to be scared of. This page, the very last page, is safe for in class, so don't feel like you need to do that unless you miss class. Okay? So starting right at the beginning, it says graph the inverse of an exponential function. So they have graphed, this is f of x equals 2 to the x. And we've done that. That's a growth exponential function. And so now in graphing the inverse, we know that the inverse, we just switch the input-output, so it becomes 0.5, negative 1, 1, 0, and 2, 1, and 4, 2. Now, you could plot those points. The other thing that you can do that I've showed you with inverses is that they're exactly directly across this line. So see how this is 1.5 squares right to there, perpendicular? Just go 1.5. That brings you to the 1 negative, a half negative 1 right there. Okay, this one, if you just go directly across, it brings you to 1, 0. This one, if you go directly across, brings you to 2, 1. And this one, if you bring it directly across, brings you to 4, 2. Okay, so you can do it that way. Now notice this is the asymptote. This line is inverted into this line, so we need to bring the asymptote right here. And that gives you an idea of what the inverse function is, which it is the log function, but we'll put the f negative 1x for right now, and then we'll come back and we'll put that log, or we'll just make a note of it in our notes. Okay, so what are the domain and ranges of the f negative 1x? Well, let's look at our exponential first. The domain for the exponential, for all exponentials, was all real numbers. It's limitless side to side. On the range, though, remember we have an asymptote here at 0. So we have I don't know which way you want to put it. It can't ever touch 0, so put a parenthesis, 0, and infinity, that it goes on and on up forever. Or you can write it as y is greater than 0. Okay? So now, knowing that it's an inverse, you know that our input-output switches. So the domain and range of the inverse will be the domain 0, infinity, or x is greater than 0. If you look here, that's what we've just said, is it can't touch this 0 here. It's got to be from this side over, so that is x is greater than 0. Okay, and then your range will be all real numbers, or infinity, infinity. Okay, does the graph f negative 1x have any asymptotes? Explain how you do know that. It's what I've already said. Yes, that the y-axis will be a vertical asymptote because the x-axis is a horizontal asymptote in the f of x. And if they're inverses, those axes are inverted. How do the values of f negative 1x change as x increases without bound? So as x increases without bound, go in this direction, what happens to your y values? They're going up. So they are going towards infinity as well. So you should write that as x arrow infinity, f of x arrow infinity. Okay? Now, a logarithm has the same base as the exponent. And that's all that this is saying up here, is that if you have an exponent with a base of 2 to the third, you would say that's equal to 8. 2 times 2 times 2 is 8. But sometimes we come along a big number, and it's a really huge number, and we say, does a certain number go into there? And that's when we use logarithms, because a logarithm is the inverse, so we can solve for the exponent. And so we would write log, the base is the same in a log as in the exponent, exponential function, so we put log 2, that's where the base goes. And then we say 8, because when we solve it, we're solving for the exponent. Okay, so the solution to log 2, 8 is 3. In other words, 2 to the third power equals 8. And I really do kind of invert them when I'm thinking about logarithms. Okay, couple special logarithms. Common logarithm has a base 10. So instead of writing log 10, we just write log x. Now you need to be aware, in your calculator, the only logarithm that you have is log base 10. There's no way to put in a different base. And we have ways to change base so you can still use your calculator. Now, a natural logarithm, instead of writing log e, remember the e, Euler's number, instead of writing log ex, we have a special button, ln. ln means log e. ln is right there below the log. Okay? So now explain in terms of logarithmic functions how to write 7 to the second equals 49 as an equivalent statement involving logarithms. Well, first thing is our base is 7. And our input because we're going to do the logarithm, our input is what our output was, so our input is 49. And our output, or what it gives us, will be the 2. So we simply write log base 7, log 7, 49, and if we hit that into a calculator, after we can put it into a calculator, once I show you that, then we would end up with an outcome of 2. Okay? Okay, explain in terms of exponential functions how to write log 1000 equals 3 as an equivalent statement involving an exponent. Well, we need to look at our base. What would our base be? When there isn't a base written, remember it's log base 10. So we know that our base is 10. Our base is 10. And since we're going to exponential now, we know our output is our input here, input 3, and output will be 1000. So in other words, these two crisscross because they form the inverse, and the base stays the same. So 10 to the third equals 1000. All right? The input of 2 to the x is an exponent, and the output is a power of 2. Describe the input and output of f of -1, log 2x. Give a specific example. Okay? So the input has to be a power of 2, and the output is an exponent that corresponds. So we could do anything that's a power of 2 for our input. 64, that's a power of 2. Log 2, 64 equals, and then figure out what is the exponent that you would use to get 2 to what power equals 64. Okay? These are the same number. You solve it. You solve that right now. And you'll have it. That's how we work them. Okay, find ln 1 over e by letting ln 1 over e equals x. Okay, so we're going to do this. ln 1 over e equals x. And now it says, write in the statement in an equivalent form that involves an exponent. Okay, well then we're going to go, let's take it back to log. ln x, ln 1 over e equals the log ex. So let's go log e 1 over e. Okay, because we know log e stands for ln. Equals x. So here what we're saying, if we go up and we think of these other things that we've done, remember the 64 comes into the answer, so the 1 over e comes into the answer, and we're really asking ourselves, e to what power equals 1 over e? Think of your negative exponents. In order to flip that e back to the top, it would become e to the negative 1. So e to the x equals e to the negative 1. We know that x equals negative 1. Please ask me tomorrow in class if that one confused you. Go back and listen to the tape again and ask specifically where your question is on that. Okay, next I love these. You just get to flip-flop inside your brain. It's kind of fun. It's a pattern, totally a pattern. It's exactly what you've been doing. We are just changing from exponent over to logarithms. So we're going to be plugging this in, log 2 to the x. Okay, so first we ask for 16 equals 2 to what power? It would be 2 to the 4th. Now we're going to plug in f of 16 for log 2x. Log 2, 16 goes in for the x. So what would that equal? 4. Okay, I didn't need to put that log 2x right there. It kind of looks confusing. Okay, so 4 would be our answer when we're asked that. So now 2 to the 6th equals 64. So f of 64 would be log 2, 64, which equals 6. Do you see the pattern happening? 1 over 32 is 2 to the negative 5th. So log 2, 1 over 32 equals negative 5. 1/8 is 2 to the negative 3rd. Log 2, 1 over 8 equals negative 3. 2 to the 0th equals 1, so log 2 to the 1 equals 0. See, you simply keep the same base as what you have in these others, but you flip-flop your input-output. Okay? Is it possible to evaluate f of 0? Why or why not? Well, let's think about that. If we have f of 0 up there, we would be saying log 2, 0. Now think back to your graph on exponents. Can we ever touch 0 on the exponential functions? If you say no, then you're right. So no, we can't evaluate for f of 0 because really we have nothing, no power that 2 can be that equals 0. It just doesn't work. Okay? 3b, for f of x equals log 2x, between which two integers does f of 40 lie? Well, let's think of that. Log 2, 40 equals, now we've got to think of our powers of 2. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, and 2 to the sixth is 64. So log 232 equals 5. Log 264 equals 6. And log 240 is in between these. So the only thing that you could say about this is that your answer, actually I shouldn't put x, x was your input of 40, your y will be between 6 and 5 and closer to that 5. Okay? Estimate g of 95 for g of x equals log x using a calculator. Okay? So all that we do, because that's a base 10 log, we simply just take our calculator, we turn it on, we press log 95, close the parenthesis and hit enter. We get 1.9777. So it's about, g of 95 is about 1.98. Okay? Oh, and then don't forget, in class, please, please, please turn them off. Second off, we'll turn them off. Anytime you're not using them. We use up a lot of batteries on these. Okay, so let's think about that. What we're saying is log 10, we don't write the 10, but I want you to think about that, 95, okay? Well, our powers of 10 to what power equals 95? We know that 10 to the second power equals 100, and we know 10 to the first power equals 10. We're really close to that 10 to the second, that's why it's 1.98, because it's so close to that, but it's between those two. Without using a calculator, explain how you know that ln 20 is greater than log 20. Well, let's go back to the meaning of it. ln 20 is log e 20, and just a regular log is log 10 20. So if we switch them back to exponential, it would be e to what power equals 20, and 10 to what power equals 20. Well, we know 10 is going to be close to 1, and 10 to the first power roughly, 1 point something. But e is a lot smaller than 10. And because e is smaller, it's like 2.7, what was it? We looked it up last time, and I shouldn't know, I apologize. Second, e equals 2.718. 2.718, you're going to have a lot more powers of it, because 2 times 2 is 4. I know this is almost 3, but even 3 times 3 is 9. So because e is so much smaller than 10, the power for e has to be so much greater. So that's why. And you probably should explain that in your own words and written out. Okay? Okay. Example 4. Logarithms aren't too bad so far, right? Okay. On example 4, all that we're doing is we're graphing this logarithm function. And so when I come up to do this, I ask myself 1/2 of 1/4. So in other words, 1/2 to what power equals 1/4. And if you say, oh, all we'd be doing is squaring it, then you're right. It's just 1/2 times 1/2 is 1/4. 1/2 to what power equals 1/2. If you say to the first power, you're good. 1/2 to what power equals 1. Anything to 0 power equals 1. 1/2 to what power equals 2/1. And I do 2/1 because I want you to see you're going to have to flip it. If you say -1, absolutely perfect. If you need to slow down and pause this every time I ask one of these. 1/2 equals 4. How about if we make that 2 squared over 1? So you'd have to flip it to get up there, so that would be a -2. And 1/2 equals 2 to the third, or 8 over 1. Again, you'd have to flip it to get there, so a -3. Now we just graph these. At 1/4, it's at 2. So here at the x on 1/4, it goes up to 2. 1/2, it's at 1. At 1, it's at 0. At 2, it's at -1. At 4, it's at -2. At 8, it's at -3. Okay. There we go. How is the graph f of x equals log 1/2 x related to the graph of log 2x from the Explorer? Why does this make sense? Okay, let's take a look at, where did it go? Front page. There's the 2x. It's going this way. And there's this one. So in other words, the 2x is coming right through here. What axis is it that they're rotated over? And let's make sense of that. 1/2 and 2 are the only differences. 1/2 to what power equals 2? It's a -1, isn't it? So does that make sense? That we just flipped it over the x-axis? I hope it does. Okay, that would be a reflection across the x-axis. Either way, it's a negative exponent there to flip it. And I'd really like you to think of the ax. We'll get into a little bit more properties here in a little bit. You'll see how that negative can come out front. But right now, just consider their absolute inverses in their base of each other, and that'll cause the reflection across the x-axis. We will get it over to where it's in that A position for you here, I think in the next lesson. Okay, so what point do the graphs log 1/2 x and log 2x have in common? 1, 0. And that should make sense from our exponential functions. Remember, in the exponential functions, we could always count on our vertex being right through the 0, 1 if it wasn't stretched. Well, if we're not stretched, we're going to be through that 1, 0 because we're an inverse. It's coming straight across our y equals x line. Okay? So anything, anytime you have a 1 in here for your x, you're going to have 0 no matter what the base is, because anything to the 0th power equals 1, and that's where the equals 1 comes in. That's our input this time. Describe the end behavior of the log 1/2 base 1/2 x. Well, the end behavior of the log base 1/2 x is that as x goes towards 0, the f of x goes to positive infinity. As x goes towards positive infinity, f of x goes towards negative infinity. The next question, how is the graph of f of x equaling log 1/2 x related to the graph of 1/2 to the x? Well, we've already talked about how logarithms are the inverses of our exponential functions. So if they have the same base, they are inverses of one another. Okay? this we'll do in class. I hope you weren't too fearful of logarithms. I hope you feel better about them now. Go back, listen to the video, and come in with specific questions for me where you get a little bit tripped up. We'll see you in class.